So this is problem 145. So we're given a couple of things. The disk is rotating with a constant angular velocity of 30 radians per second. And I will write this here, omega equals 30 radians per second. And we're told that the radius of the disk is 150 millimeters. So if I were to draw a line from the center to on the edge, the radius will be 150 millimeters. We're told that the oil under the disk has a thickness of 0.15 millimeters. So the thickness of oil, I'm not really sure how I'm going to write, I'm just going to write thickness, is 0.15 millimeters. And then we're told to assume that the velocity profile is linear, so that's good, and that the viscosity of the oil is equal to 0.428 Pascal times second. So the units given in the book are newtons times seconds per meter squared, but we know newtons per meter squared is Pascal, so I think it's easier if I just call it Pascal times second. And we want to know the torque that's required to rotate this disk with that angular velocity. So, how do we start this problem? First off, which fluid property do you think we are focusing on when trying to solve this problem? Is it a density problem? Is it a compressibility problem? Is it a surface tension problem?
I'm sorry, can you repeat that? I was busy writing.
It's okay. What type of problem is this? What fluid property are we trying to solve with this problem? Or are we trying to use? Sorry?
Viscosity?
Yeah, it's a viscosity problem, okay? So we're not being asked to compute anything related to density, anything related to compressibility. It's simply a viscosity problem. So if it's a viscosity problem, I'd like to point you to Newton's law of viscosity. Newton's law of viscosity tells us that the shear stress applied in a fluid is proportional to the strain rate. Now, in lecture for week number 2, I explained how the strain rate can actually be calculated by taking the derivative of velocity with respect to depth, and that the factor of proportionality is what we call viscosity or dynamic viscosity. So, given this information, we are asked to find the torque, okay? Now, we can still find the torque by simply plugging numbers into here, but the problem is that we need to know exactly what we are trying to plug into the equation. So what I'm going to do first is I'm going to first try to figure out how to relate, right, my angular velocity to this velocity gradient, okay? So let's think about it first. We know a couple of things, right? We know that this disk is rotating, okay? Now the disk is rotating and we are given the angular velocity of this disk. That means that the fluid that's in contact with the disk is going to rotate with the disk. That's what we call the no-slip condition. So I'm going to try to draw this disk from above. If I were to draw this disk in top view, what I have is a disk. And let's say I want to draw an imaginary line from the center all the way to the end of the disk. I'm going to call this line my radius line. It's simply an axis that travels over the radius. Now the disk is rotating, right? So we know that the disk has an angular velocity of 30 radians per second. So now if I were to ask you, this disk is rotating at 30 radians per second. What do you think is the velocity? And here, don't think about rotation. Think about simply linear velocity. What do you think is the velocity of a fluid particle that's located right at the center of this disk?
0.
0, right? The velocity of this fluid particle is simply, we're just going to call it 0. What about the velocity of a fluid particle at the very edge of the disk? So the disk is rotating. So if I were to quantify this velocity at the edge of the disk, what would the velocity be?
30 radians per second.
Not angular velocity, just linear velocity. You give me angular velocity, then that's good. What about linear velocity? If I want to quantify only the linear velocity, how do I convert from angular velocity to a linear value? Think of it in terms of tangential velocity and angular velocity.
Will you multiply it by the radius?
Exactly, right? We know the velocity will be equal to the angular velocity times the radius, or in this case, the radius represents your distance along the r-axis. So for the velocity at the edge, we would have our angular velocity of 30 radians per second multiplied by the distance between the center and my edge, which is 150 millimeters. So it'll be 30 times 150 millimeters per second. And the velocity of any particle in between should be equal to the angular velocity of 30 meters per second, or 30 radians per second, multiplied by whatever distance this particle is from the center. Does that make sense so far?
Yes.
Okay. So what I'm going to do is I'm going to express a relationship of my velocity to be equal to my angular velocity, which is 30, times r, where r is any distance from the center. And I'm going to change the radius to capital R so we don't confuse it with our variable. So what I'm looking at here is I'm looking at a constant angular velocity and a variable r. That means that the velocity of a fluid particle will vary with the location of the particle relative to the center. So that's my relationship. My relationship is that my velocity is equal to angular velocity times r, where r is a distance from the center. If I want to start to plug in some numbers, I know that angular velocity is 30 radians per second, so I can write this as 30 times r. And this will be the equation for my velocity. So now I can go to my velocity profile. If you remember back in the lecture, we tried to solve velocity profiles, and we said that one common assumption is that if our thickness of a fluid is very, very, very small, then we can take the velocity profile to be linear. And that's exactly what this problem is telling us to assume. We're told to assume that the velocity profile of our fluid is linear. So I was looking at this disk from above, right? This is a top view. But now let me look at it from the side. This is a profile view. If I were to look at the disk from the side, what I essentially have is my disk, again, looking at it from the side, and it is rotating in this direction. Because it is rotating in this direction, my oil, and I'm going to exaggerate the thickness here, my oil will be moving in the direction of rotation as well. Okay? So I'm just looking at this disk from the profile view, and what I see is that the disk is rotating, and as my disk rotates, so does my oil rotate along with the disk. So if I am asked to plot the velocity profile of the oil, and I'm told in the problem to assume that it is linear, then I can safely say that the velocity profile of the oil looks like this, like a linear velocity profile. And now, because this is a linear velocity profile, then we can come up with an easy relationship for du dy. So if this is my linear velocity profile, we know that this is my y-axis. And we also know that the thickness of the fluid is 0.15 millimeters. So I'm going to write down the thickness here as 0.15 millimeters, and that is the measurement of the total thickness of the fluid. Okay? For linear velocity profiles, we know the velocity at the top is the maximum velocity, which we already know that can be calculated by 30R. So Umax equals 30R. And the velocity at the bottom in a linear velocity profile is simply 0. So we're dealing with two velocity profiles. We had a top velocity profile, which is related to the rotation and the distance from the center. We have a bottom velocity profile, which is related to the thickness and the distance from the bottom. So that's my velocity profile. If my velocity profile is linear, then I can say that du, di, the rate of change is a constant, right? If my velocity profile is linear, then this velocity profile will increase with a rate of Umax, right, over my thickness y. So what is my Umax? My Umax I already calculated, 30R. And then my thickness becomes my 0.15 millimeters.